Hello students, my name is Shashank Shekhar. So today we'll start alkene. Okay, so in the previous class we have completed alkene. We have seen the preparation, right? We have seen the reactions also and plus their configuration. Now today we'll start alkene. We will see the structure of alkene, the orbital diagram of alkene, look at their nomenclature, and at last we will see some problems related to what we studied till today. Okay, so first of all, what are alkenes we should know. So in alkanes, we have confirmed that alkanes are those compounds which don't have any, they don't have any unsaturated bond. Okay, means unsaturated carbon. I would say they don't have any unsaturated carbon. Whereas in case of alkene, we have unsaturated carbon, and it is due the unsaturation is due to the double bond, right? So in alkane, we have no double bond, whereas alkene we have double bond, and we have the general formula of CnH2n. Now, alkenes are also known as olefins. Okay, so this thing is important because these two things you have already studied in class 10th. If you have not studied, then you can just go through this. But this point is important. Now, why it is important? Why I'm saying that this name is important? Because sometimes in the questions, you may be referred alkenes with the help of the name olefins. Okay, and that may confuse you at that time if you are unaware about this name. Okay, so you should be aware about this name of alkene, common name of alkene, that it is also named as olefin. Okay, now if you talk about the structure, so carbon-carbon double bond consists of a strong sigma bond. So there are two bonds between carbon and carbon. If they are doubly bonded, so if there are two bonds, the first one is sigma bond, which has a bond enthalpy of 397 kilojoule per mole, and it is there due to the overlap of sp2 hybridized orbital of one carbon with the sp2 hybridized orbital of other carbon. Now there is also a pi bond. The second bond is a pi bond, and the bond enthalpy for that bond is 284 kilojoule per mole. So you can clearly see that sigma bond is thermodynamically stable than the pi bond. Okay, now how it is obtained, how this pi bond is formed. So it is formed to the side or lateral overlap of the empty p orbital. Not empty, it is formed to the side overlap of p orbital. So I would specifically say that 2p orbital of the two carbons. Since we have the sp2 hybridization, so one of the p orbital is left out, right? And that left out carbon has the left out orbital has electrons in it. Now these two orbitals overlap with each other to form the pi bond, and the double bond is shorter than the bond length, and it is 134 picometer, whereas the carbon-carbon single bond is 154 picometer. What is the reason behind it? What is the reason behind shortening of length? It is due to greater bond order, because carbon-carbon have greater bond order. In case of double bond, it has simply a bond order of 2. So the bond length is 134 picometer. When this bond order is decreased in case of single bond, it is 154 picometer. Okay. Now, it is important to remember the type of bonding. So it is very, very important. Why? Because you may get confused and question may be asked on the statemental basis that you have to predict that which kind of bonding is present there. So you should be very aware about this carbon-carbon double bond. That is, carbon-carbon double bond includes the head-on-head overlap of sp2 hybridized orbital and the side-on-side or lateral, means these two things are present as parallel to each other, right? And they overlap, and that results in the pi bond. And one more thing, that this bond enthalpy clearly indicates that the sigma bond is thermodynamically stable than the pi bond. Okay. Now, the pi bond is weaker, we know that, and it is weaker due to the poor sidewise overlap between the two p orbitals, because that overlap is sidewise overlap or not head-on-head overlap, and we already know that head-on-head overlap are much more efficient, okay, as compared to the side-on-side overlap. Head-on-head overlap are more efficient. Okay, now since it is more efficient, so that results in more stronger bond. So Of course, we know that from chemical bonding, from valence bond theory, that greater is the extent of the bond overlap, more is your bond stronger. Now, since this pi bond that we're talking about are weaker, it means the electrons between the two carbon atom, okay, that means the pi electrons between the two carbon atoms are held loosely, okay, because it is a weak bond, it can be broken easily. It means the electrons are held loosely, right? And now this loosely mobile electrons, so we are calling it mobile electrons because now they are more mobile in comparison to the sigma bond. Okay, they are more mobile in comparison to the sigma bond because the overlapping is not fair enough. Now, due to this reason, they are electron rich in nature. Okay, therefore, alkenes are easily attacked by reagents or compound which are in search of electrons. So, we can say that since it is electron rich, therefore it can act as an electrophile. Okay, what are electrophile? The electron rich species are called as electrophile, and those species which are lacking electrons or are called nucleophiles are in search of electrons. They may attack this pi bond. So the same thing is written that such reagents are called electrophilic reagent, which contain a pair of electrons available for the incoming positive or nucleophile. Okay, is this clear? Now, you should keep this in mind. Now we are building up the reaction mechanism, right? So this small things you should remember because this totally builds up the chemical reaction and brings us to the whole picture. Now the presence of weaker pi bond makes alkene unstable molecule in compared to the alkane. Thus alkenes can be changed into single bond compound by combining with electrophilic reagent. So what is being said here is that since we know that the pi bond is weaker, okay, than sigma bond, that means that your alkene has less stability than the alkanes because of the presence of pi bond in alkenes. Now, due to this reason, this pi bond or this double bond can be converted into single bond. Okay, they can be converted into single bond. How? By reacting it with electrophilic reagent. So we will see how this reaction goes. So you will see it. But for now, you should remember that upon reaction with electrophilic reagent, the double bond is converted into single bond. Okay, so here is a comparison of the carbon-carbon double bond. It is 681 kilojoule per mole, and it is greater than the carbon-carbon single bond, which is 348 kilojoule per mole. Now you will say that, okay, you have said that the pi bond, the presence of pi bond makes alkene unstable as compared to alkene, but here we are seeing that the bond enthalpy of the double bond is greater than the single bond. Okay, so let me make one thing clear. Now, instead of this double bond, there are two single bonds there, right? So if I say that this is the strength of two bonds, okay, this is the strength of two bonds, 681 kilojoule per mole, and this is the strength of one bond. Now, there are similarly four bonds there, okay. If you compare it with ethene, it has only one carbon-carbon single bond and one carbon-carbon double bond. But in case of ethane, the bond enthalpy of one carbon-carbon single bond is 348. Now there are other bonds also, carbon and hydrogen, and those are sigma bond. Clear? And therefore, when you add those single bond energy, then that would result in more bond enthalpy as compared to carbon-carbon double bond. Okay? So this you should not be confused with that. Here we are talking about the two bonds. It is the energy that is required or the enthalpy change that is occurring during the breaking of two bonds. Whereas in this case, we are seeing the energy change or the enthalpy change, we are breaking one single bond. Now this is the structure. Now this would make the things clear. See, this is a carbon here. Okay, here it is a carbon and here is a carbon. Right. Now we know that this carbon and this carbon are sp2 hybridized. Okay, see, one s orbital and two p orbital must have combined, and that would resulted in three orbitals, 1 2, and 3. Okay. Here also on the right hand side the carbon does the same. Now there is a head-on-head overlap between the sp2 hybridized orbital of the left carbon and the sp2 hybridized orbital of the right carbon. That resulted in a sigma bond between this carbon and this carbon. Now the small lobes that are present here are called as anti-bonding. Okay, so this is anti-bonding. So if you want, you can show them. If it's asked in the exam to show the anti-bonding, then you can do it. If it is not asked, then you don't have to do so. Okay, there is no compulsion of drawing the anti-bonding. You have just to draw the bonding part. Now the other two sp2 hybridized orbital, this one and this one, they just overlap with the hydrogen s orbital. Okay, s orbital of hydrogen is overlapped with this, and there are 4 such overlaps, so 4 such bonds are formed. Now 2 p orbitals are in the hybridized state and 1 p orbital is in the pure state. Now those 2 pure p orbital, they do a side on side overlap. Okay, they do a side on side overlap, so it is mentioned here that pp side on side overlap is happening here, and that results in a pi bond. Now after this overlap we get kind of this thing. Okay, see, okay, so this is called a pi cloud. Okay, this is called a pi cloud. Now if I talk about the bond parameters, so it is mentioned here that the carbon-carbon double bond is 134 picometer. Okay, whereas this carbon-hydrogen bond is 110 picometer. Now if I ask you that compare the bond length of carbon-hydrogen, means the bond length between carbon and hydrogen in case of alkane and in case of alkene. So you will find that in case of alkane, the carbon-hydrogen bond is longer. Okay, it is longer. Whereas in case of alkene, the carbon-hydrogen bond is shorter. What is the reason behind it? The reason behind it is very simple. Since in case of carbon-carbon double bond, the hybridized orbital which is involved in making bond with hydrogen is sp2 hybridized. So it will have a s character of percentage s character of 33%. Whereas in sp3, the percentage s character will be 25%. It means that in alkene, the s character is more. Okay, now a compound which has more s character, or the orbital which has more s character, will be more electronegative because s orbital are more electronegative in nature. So it will attract the electron clouds more towards it, resulting in a small bond. Okay, so this should be kept in your mind that carbon-hydrogen single bond is longer in case of alkane in compared to the carbon-hydrogen bond in case of alkene. Here the bond angle is not accurate. It is 121.7 degrees and not 120 degrees. The reason is also very obvious, because in this bond, okay, here, if you talk about this one, there is a repulsion between a pi bond and a sigma bond, or you would say there is repulsion between a double bond and a single bond. So double bond has more electron density, okay, as compared to the single bond. So therefore it pushes this single bond more outward. Whereas in this case, if you talk about the angle which is 116.6 degrees, here the repulsion is between two single bonds. Okay, the repulsion is between two single bonds, and that repulsion extent is lower as compared to the double bond and single bond repulsion. So therefore it is kind of squeezed, and the angle is less as compared to 120 degrees or the ideal condition, whereas this angle is more, which is 121.7 degrees. Okay, is this thing clear to you? So we have come a far path. So we have defined the structure very well. We have seen the bound parameters also, and all these things are important to maintain, or you would not maintain, I would say, to study forward. Okay, the structure and all is very important to study forward the reactivity of the alkene, because all of this reactivity and all is closely related to the structure, that how the structure is there, and the structure will define that how the incoming nucleophile or electrophile will react with this alkene. Now, next thing, we will move to a common thing, that is nomenclature. So, although it looks easy at first view, but believe me, it is important. Okay, and sometimes it may create a chaotic scene. Okay, some questions are there which may create a chaotic scene, and you would find it difficult to solve the easy question of nomenclature. So you should be aware about the nomenclature each and every time you deal with a functional group. So to name the alkene, the process is simple and is general. So first of all, we look for the longest chain. Okay, we look for the longest chain, and the longest chain is first selected, and the ane is the ane of the alkane is replaced by ene. Okay, it's replaced by ene. So here are some examples for it. So we have propane. Propane is converted to a double compound containing one double bond. So its name would be propene. What about this? So it is butane derivative. One hydrogen is removed. So we have written it but 1 in. Okay, so I would suggest you that it would be more appropriate if you write it in this form. Okay, but 1 in. So why here it is not written prop 1 in? Because if you keep this double bond on this side or either on this side, that would result in the same name. Okay, you can't change the name to prop 2 in. It is nearly impossible. So it is absolutely impossible. So we have written in this way so that since there is no chance of shifting double bond away from the first position. But if you want, you can write it prop 1 in. There is no mistake in writing that in that form. Okay, next is but 1 in. Okay, what about the third one? So here we have shifted the double bond in middle, so its name would be but 2 in. So 1 2 at the second carbon we have double bond. Either you count from the right side or you count from the left side. Yeah, what about counting? So in the second example we have counted from the right side so that the functional group comes first. Whereas in third example we can count it from the either side because the double bond is present on a symmetrical side. What about the fourth one? So we have two double bonds here. So again, the two double bonds are kind of symmetrical. You can count it from the either side. So let us count it from the left side, suppose. So but, because 4 carbons are there, 1, 3 diene. So two double bonds, so diene. Okay, and then 1 and 3 are defining the position of this double bond. What about this compound? So again, the longest chain can be considered. So there are two possible longest chain. Either you start from the right or you start from the left. But we want the functional group earlier, so we will start from the left. Okay. So 1, 2, and 3. At first position, so this is propane. 1, 2, 3, 3 carbons propane. So at first position we have double bond. So prop 1 in. First, this is clear. And at second position we have methyl group attached to the carbon. So 2 methyl prop 1 in. Okay. Name would be 2 methyl prop 1 in. Next is this one. So again, we can have two possibilities. Either we can go it in this way and move down or remain straight. So this both compound will be same. Now the counting will be started from the left hand side because functional group falls here first. So 1, 2, 3, 4. So I'm counting the straight chain. So 4 carbons are there. So the root name would be but. And at first position we have ene, that is alkene. So but 1 in, and at the third position we have methyl. 1, 2, 3. So it's counted from the left hand side. So at third position we have methyl. So 3 methyl but 1 in. Okay. Now next question, we have to count the number of sigma bond and pi bond which will be given in the structure 1 to 6, and you have to write the IUPAC name of the compound. So here are the compounds. So in this, what you have to do, you have to count the number of pi bonds and sigma bond. So first I will do the nomenclature. Okay, first we will do the nomenclature of each of these. So let us see. So how you will name it? So this is the whole compound. Just look at this, it is going here, here, and here. Okay. So there are two ways to do it. Okay, there are two ways to count it. First of all, let us find the longest chain. So you can go from this carbon or this carbon. Okay, so I think we should go from this carbon because it has two carbons here. Okay, it has two carbons here. So how you will name it? So first way is this, that you can count from here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10. Now, which side should we start? We should start counting from. So if you count it from the downside, so 1, 2, 3, 4. On the fourth position, we have double bond. If you count from the left hand side, so 1, 2, 3. So on third position, we have double bond. So we will count it from the left hand side. Okay. Now, what is the number of carbon that we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is decane. Okay, decane. So I will use just the root, that is dec. So just that dec is there. Now, how many substituents are there? So on the first carbon, we have one methyl substituent, and on the eighth carbon, we have one more methyl substituent. So it name would go. Say this is the second carbon. So on the second and eighth carbon, we have substituents methyl, and on the 1, 2, 3, 4, 5, fourth and fifth carbon, we have alkene as a substituent. So its name would be 2,8 dimethyl. Okay, 2,8 dimethyl dec 4,5 diene. Okay, its name would be 2,8 dimethyl dec 4,5 diene. Clear? Now let us count the number of sigma bond and pi bond. Okay, number of pi bond is very easy. One pi bond here and second pi bond here. So two pi bonds are present. What about the sigma bond? First of all, let us count the number of carbon-carbon sigma bond. So this carbon has two carbon attached to it, two sigma bonds. 3, 4, 5, 6, 7, 8, okay, 9, 10 here. And this carbon has one more carbon attached to it, so 11. Okay, 11 carbon-carbon sigma bond. Now what about the carbon-hydrogen sigma bond? So whatever will be the number of hydrogen will be the number of carbon-hydrogen sigma bond. So 3 to just 6, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 and 5 is how much? It is 22. 22 plus 11, that is 33. Okay, so 33 sigma bonds and 2 pi bonds. So same thing is written, 33 sigma bonds and 2 pi bonds. What about this? What would be the name of this? So since it is symmetrical, you can count it from the either side. So let us count it from the left hand side. 1, 2, 3, 4, 5, 6, 7, and 8. 8 carbons are there. Okay, so hept will be the root name for it. Okay, sorry, oct will be the root name for it. And at first position we have double bond, second we have double bond, third we have double bond, fourth we have double bond. So first, third, 1, 2, 3, 4, 5, 6, 7. So 1, 3, 5, 7. Okay, 1, 3, 5, 7. Oct 1, 3, 5, 7 tetraene. So this will be the name. Okay, octane. For 8 carbons we have oct. For 4 double bonds we have 4 positions, that is 1, 3, 5, 7, and for 4 double bonds we have put tetra. So oct 1, 3, 5, 7 tetraene. Clear? What is the number of pi bond? Very easy to count. Number of pi bond is 1, 2, 3, 4. What is the number of sigma bond? So first let us count the number of sigma bond between carbon-carbon. So 1 carbon bond, 2 carbon bond, 3, 4, 5, 6, 7. So 7 carbon-carbon sigma bond. What about the hydrogen bonds? So here 2 hydrogens will be present. Okay. So 2, first of all 2. Then here one hydrogen bond will be present. So 3. Here also 1, 4, 5, 6, 7, 8, 9, 10. So 10 sigma bonds of carbon hydrogen, and 7 were already there. 1, 2, 3, 4, 5, 6, 7. Okay. 4, 5, 6, 7, 8. So 8 are there or 7 are there? Let us count it one more time. 1, 2, 3, 4, 5, 6, 7. Okay, 7 sigma carbon sigma bond, and 10 were carbon hydrogen sigma bond. So totally 17 sigma bonds and 4 pi bonds. So 17 sigma bonds and 4 pi bonds. And the name would be oct 1357 tetraene. What about this? What about its name? Say. Okay, so let us count this. So this carbon is attached to 2 such substituents. Okay, so 1, 2, 3. So 2 propane groups are attached. Propyl groups are attached to this carbon. So let us take one of these at the parent chain, and we'll start the counting from left because functional group falls first. So 1, 2, 3, 4, 5. 5 carbons are there. Okay, 5 carbons are there. So the root name will contain pent. Okay, root name will contain pent. And at the second carbon we have a propyl group. So 2 propyl, pent, 1 in. Okay, because at first position we have alkene, so 1 in. Therefore its name would be 2 propyl, pent, 1 in. What is the number of carbon? What is the number of pi bond? Of course it is 1. Very clear. What is the number of sigma bonds? So first let us count the number of carbon sigma bond. So 1, 2, okay, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6, 7. 7 carbon bonds. What is a hydrogen bond? So just count the number of hydrogen. 2 to 4 to 6, 6 and 3, 9. Okay, but 7 are repeated twice. So 7 to the 14 and to 16. So 16 and 7, how much? It will be 23. So carbon. So sigma bonds is 23 and pi bonds is 1. Okay, clear? What about this? What is the name of this? So first let us count the number of carbon sigma. Count the number of carbon. Count the number such that the longest chain can be obtained. So we can do it from this side. I think this would be good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 carbon. I think this is the longest chain. Okay. You can count it from here also. 1, 2, 3, 4, 5, 6, 7, 8, 9. No. So this is the longest chain only. 10. Okay. 10 carbon containing chain is the longest chain. Right? What about the functional groups? So first let us talk about the substituents. So at first we have one methyl group and second we have one methyl group, third, fourth, fifth, sixth we have another methyl group. So at second and sixth we have methyl group, whereas on 1, 2, 3, 4, on fourth we have ethyl group. Now ethyl comes first in the alphabet, so 4 ethyl and 1, 2, 3, 4, 5, 6. So 4 ethyl, 2, 6, dimethyl, dec, 1, 2, 3, 4, dec, 4 in. Okay, so the name would be 2, 3, 4, 4 ethyl, 2, 6, dimethyl, dec, 4 in. Clear? Okay. What is the number of carbon sigma bond? So 1, this, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 carbon bonds. What about carbon hydrogen? So 3 to 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. 19, 18, 19, 20, 22, 23, 24, 25, 26 and 29. 29 here and 11 were early, 13 were earlier. Let us count this all. What is the number of pi bonds? It is 1. Okay. So that brings us to 41 sigma bonds and 1 pi bond. Okay, so this was all for today's lecture. With this, I end my lecture. Thank you.